Hey everyone, in this video, let's take a look at question 329, longest increasing path in a matrix. This is part of our blind 75 list of questions, so let's begin. In this question, you're given an m by n integers matrix, so matrix array, which is m by n, and you want to return the length of the longest increasing path in matrix. From each cell, you can either move left, right, up, or down, and you cannot move diagonally or go out of bounds. Basically here, the longest path is 1, 2, 6, and 9. That's increasing. It looks like it has to be strictly increasing. You can see that this path is a length of 4, which we return here. And here it's 3, 4, 5, 6, similarly a length of 4. And at the minimum, actually, the path will be 1, right? So at the minimum, we can return a length of 1. Okay, so this is our basic like graph type, not graph, but like matrix type question. But we will use one of the graph type algorithms. Specifically, we can use DFS. But why did it come up with DFS? Well, usually when you see these types of problems, then a DFS is a good choice whenever you want to find the maximum something, the minimum something, especially when it relates to some sort of matrix or some sort of grid of numbers. So that's one thing. But another thing is it just makes sense, right? Like, for example, if we had like 1 over here, then I want to try to go as far as I can along this matrix to find out if I can maybe extend this one and form a longest path. So that's how kind of DFS comes to my mind. Now, this question, if you've done the number of islands question, you know that in that one, we also did DFS. But one of the differences there was that we did not have to do DFS off of every single cell, right? In the number of islands question, we only did DFS from the islands themselves, basically wherever the entry was a 1. Here, we don't really have any of that like constraint, right? Here, it's not really clear to me that we can only do DFS from a specific location. Really here, we have to do DFS from all of these cells because there's nothing that tells me that, like only I can do DFS from one location. So in this case, I have to do DFS from every single cell. So that's something that's kind of different based on compared to like number of islands. Now, otherwise, if you just think about this question, it's not really that hard if you have done these types of questions before. So I know this question is labeled as hard, but if you've really done these types of questions before, then they often try to follow like the same sort of convention or the same sort of structure in terms of the code. But let's take a look at how this can work, right? So let's assume that we start off over here. Obviously, we won't start our DFS call from here. We'll start from over here. But let's just assume that we start from here. So then what can we do? Well, we know our minimum. At minimum, our answer will be 1, right? At minimum, our answer will be 1. What can we do? Well, from this location here, I can travel either up towards the 6, right towards the 1, or left towards the 2. Now, I don't necessarily know which one of these is going to give me the longest path, right? I don't even know if any of these are valid. For example, if I go to this side over here, this is not valid, right? Because basically I cannot form anything here. 1 and 1, this does not work. 1 and 6 work, 1 and 2 work, but 1 and 1 does not work. Okay, so we have that information. So we need to somehow check like to see if the path is even valid in the first place. And we'll talk about how we can do that. Let's say we go to the 2 here. Okay, if we go to the 2, then the 2 works. Okay, cool. Then the 6 also works. The 9 also works. Now, if we go outside the 9, then we're like basically like out of bounds, right? So if we go anywhere over here, we're out of bounds. So what can we have our function return? What can we have our recursive function return? And if you really think about this one, let's just say I'm at like a single cell, right? 9, and I go out of bounds. So then if I go out of bounds, what is the length of the longest sequence? Well, you may think it's like 0, right? Because we're going out of bounds. But in reality, the length of the sequence over here is 0. Like if you go out of bounds, the length can be 0. But when we include this 9 over here, then the length of the longest sequence is 1. Over here, the length of the longest sequence is basically a 1. Now we backtrack. Now we're on the 6 here. What is the length of the longest sequence? Well, whatever this will return the length of the longest sequence from 9 and onwards. So we see from 9 and onwards, the length of the longest sequence was 1. And so if we are adding 6 to the sequence, then it should be 1 plus whatever this one was. So now it would be 2. Again, let's say we're at the 2 now, and we want to figure out what is the length of the longest sequence. Well, when we did a recursive call, this call over here from the 6, from right above, will return me the number 2. It will return me the number 2. Now what I can understand from this is that if it returns me the number 2, which means that it is increasing, then I'm going to add my 2 to this list, and so it will become 3 here. The length of the longest sequence up till this point, from 2 and onwards, is 3. Again, now when I come back to 1 here, then I can see that from my left-hand recursive call, I was able to extend my longest sequence by 3 units. Now, if I want to include this 1 here, which I do, then I can include it, add in 1 more. So get a total of 4. So that's how we go about creating our longest sequences. And we'll basically keep track of the maximum one and return it in the very end. So let's take a look at how we can do this. And we like to follow our specific format or type of code structure we like to use for these types of problems. So first thing I do is I always rename this to grid, and it's an easier name to just work with. And then I like to determine what my rows and calls are. And I can do this as so. Take the length of the grid and length of the grid as 0. So that's my M and N. And then I like to go through my rows and calls, call in range 0 to calls. And then what? Well, we need to do our DFS call, right? And we don't have a condition like if grid at row call equal 1, then do our DFS call. But actually here we need to do it from every single cell. So I can do something like self.helper. I don't know what I'm going to put in here, but this will be my helper, right? My DFS call, and this should return to me the list, like the longest increasing path starting from this index, starting from this cell. Now, let's say it returns to me like some sort of variable, right? Like some sort of variable path. Okay, so this is an integer. Well, now I need to basically check this path with my global path to see which one is longer. So maybe I'll have a global path here, call it res, and I'll set that equal to 1. And then basically what I can do here is I can do res is equal to maximum of res, or the path that I got from a recursive call here. And then at the very end, I can go ahead and return res. Okay, so that's our driver function. Let's see what we can pass into the helper. And a lot of the time, our structure is going to remain the same. So what do we need? So we need the grid, we need the row and the column. What else do we need? Well, if you think about this, right, like if we're on the 2 here, how do I know that like this is an increasing path? Well, I need to know the previous element, right? Because if I'm on the 2 here, the only way in which I can maybe even consider this path is if the previous number was less than my current number, right? Which means that I can maybe go ahead and do my recursion here. If I can't do that, like if this number was a 0, then I can't even do my recursion. I just have to return. So I need to know what my previous number is. I will do that previous val. So I think that's all we need for now, but let's see if we need anything later on. Okay, so first thing that we want to check is whether we're out of bounds or not, right? And so this is what we always do in these types of questions. You can check number of islands. We always like to follow this type of format. So what we will do here is I'll actually just redefine my grid, my rows and calls. And this could actually be passed in, but I just redefine them because I don't want my helper to be too large. Okay, so what are some of the conditions we have to check? Well, we have our like tiny little formula that we like to use. So we say if row is less than 0, or row is greater or equal to rows, column is less than 0, or column greater or equal to calls. If this is the case, then we're out of bounds. If we're out of bounds, what do we say? Well, if we're out of bounds, basically there's no path, right? So the length is 0. Length here would be 0. What about otherwise? Well, otherwise, I'm on a cell, and I want to check if the previous cell was smaller than my existing cell. If it's not smaller, then I can't really do anything. I can't recurse from here, right? So for example, it's like if we go from 6 and we go down to 1, well, this is not an increasing path, so I can't actually recurse from here. What can we do? We can check if grid at row and call, if this is less than my previous val, right? If it's less than or equal to less than or equal to my previous val, so we have something like this, then it doesn't work. We can return 0 here as well. This means that from this index, we can't form an increasing path. Okay? So now that we have our base conditions out of the way, what can we do? Well, now we can go ahead and we can recurse. Let's assume we're at the 6. Now we can recurse up, right, down, left. So let's actually just define that. So I will just define this like this, previous val, and then we will fill this in. Okay, so let's do left, right, up, and then down. Okay, so if I'm going left, my column decreases by 1. If I'm going right, my column increases by 1. If I'm going up, my row decreases by 1. If I'm going down, my row increases by 1. Now what is previous val here? Well, previous val should now be my current value, right? This is what I'm passing in. Like I'm going from 6 to 9, so I need to pass in the previous val of 9 as 6. So it'll be the current val, which is grid at row and call. And actually, maybe let me just define, because I'm using grid at row and call quite a bit, let me just define like OG here. I will call OG as an original, as grid at row and call. And then I will reset this to just be OG. OG. Okay, perfect. But now now what do I know? So if I'm at 6, right? So if I'm at 6, so let me go back here and I'll actually remove all of this. I need to add in this again. Okay, so if I'm at 6, then I want to know what is the longest path starting here, starting here, starting here, starting here. So what would these return? Well, automatically we know that for the bottom case here and this case here, it will return 0. Why? Because the number is the same or less. In this case, it's less, the 1 is less, and 6 is the same. So that's why it'll return 0. What about here, 9? Well, 9, we can see that from 9, we can at least do like, form 1, right? Like 1 is the minimum we can do here, because 9 at least we can extend, at least like the previous one, we can extend here. So this will be 9, right? Now, let's assume that this is actually a 10 here, just for argument's sake. Now, what about the 8? What would the 8 return? Well, from the 8, we can actually go down and reach this 10 over here, right? So this 10 and this 8 combined would give us a value of 2. So then this thing here would return, what would it return? Well, it would be 1 and 2, the maximum of these, right? Plus the 6, because I want to extend 6 into the path here. So it would be the maximum of 1 and 2, which is 2, and then added 1, which is 3, which means this is the longest path, 6, 8, and then 10. So let's see how we can do that. We can do result is equal to maximum of left, right, up and down. But not just this, we want to add the current path, so we will do +1. And that's pretty much all there is. And then we will return result to whatever the caller was, because this will return the maximum path at this specific index. So that's basically all we have. So now let's go ahead and run this. So we have grid, roll call, previous val. So what should I pass in as my previous val? Well, initially, I need to pass in something such that the number I'm currently on is greater than previous val. So what's a number that's everything is greater than? Well, it would be minus infinity, right? So minus infinity. So now let's go ahead and run this code on our test cases to see if we made any mistakes. Okay, so we haven't. So let's go ahead and submit this. Okay, and you'll see eventually that we'll get a time limit exceeded error. Now, I will discuss the time limit exceeded error in just a moment, but one more thing I want to discuss here is, if you notice in like our other problems, what we often did is, when we went from 1 to, and then it's possible we could have went back, right? So it's possible we could have had an infinite loop. We had to check this in number of items. We had to check this in other graph problems and other grid problems. Why didn't we have to check that here? Is it possible for us to go from 1 and then 6 and then back to 1? And then basically this repeats infinity. It just repeats back and forth. Is this possible? Do we have to check for this? Well, it's possible that we go back and forth, but notice how if we go back and forth, we will just return right over here. So realistically, like, we don't even need to check this because we will return right away. So we will not have the case where we just infinitely recurse. We will maybe go from 1 to 6 and then 6 back to 1, but then that's it. We will not keep going again and again. If we want, we could actually make this a little bit easier, just to kind of follow our convention. In that, what we do is we set grid at row and call equal to like some arbitrary value here. And then we can check if grid at row and call is equal to this arbitrary value. That means we visited this in the past, so we'll just return 0. And then once we are done this, we can just reset grid at row and call back to what it originally was. And so we can try this out, and we'll see that this also works, but it actually is not needed. And so here, I actually made a mistake because, yeah, grid at row and call. So here, maybe I need to do something like -1. I need to add in an integer here. Between string and int, yeah, so this one should actually be -1. And it looks like I can do that because we only have positives. Okay, sure. Yeah, so this is like something I can check for, but I don't really need to, but you know, I can check for it just to kind of maintain our structure of how we like to do these problems. Now, the last thing is time limit exceeded. So the solution actually used to work before, like in 2021, but after they added in this, we have to do memoization to basically fix it. So in order for us to add memoization, what we need to do is, first of all, we can pass in a dictionary here, which will essentially be our memo, and then here, and all of these locations here, and we'll just pass in the memo part of our function. Okay. Now what do we need to do? Well, now we can basically check if row call in memo, then we can just return memo at roll call. Otherwise, we need to cache this. So we will do memo at roll call is equal to res, which is our answer. And then we can just return memo at roll call, which is res in this case. Let's go ahead and run this test case to see if we pass. Okay, we'll go ahead and submit. And we can see that it's actually taking a little bit more longer than it needs to, right? It's taking about 4 seconds. So even after memoization, why is it so slow? Well, if you take a look at what we're doing here, we're creating a new memo every single time, right? We're creating a new memo on every single different cell. But do we really need to do this? Well, we don't, right? Because let's assume like we have the answer to this cell over here, this cell 6 over here. Maybe we got it in some sort of function. Well, if we have the answer to this cell over here, then that has to be the best answer, right? It has to be the best one because from our DFS call, we'll try to visit every single cell we can. So if this is the best call, if this is the best answer, then we don't need to create a new memo every single time. We can actually just create a global memo and just reuse that in subsequent cell calls. So we can do memo as dictionary here, and then we can see that if we do it now, it is much faster. So we should be able to finish it within less than 500 milliseconds, which we do. So that's one of the things that we should keep in mind for. If you can do memoization, make sure we don't create a new memo every time if you don't need to. Okay, so what is the time and space here? So the time, basically, we're just going through the entire grid. And you can see that memo would basically make us back out very early if we already know the answer. So you can think of it as worst cases like O of m times n, and kind of the same thing for the memo. In terms of the space complexity, it would also be O of m times m. Okay, thanks for watching.